What we're doing today is talking about the stress tensor.
The screen's supposed to be on.
Are you going to do anything but complain today? Okay. The stress tensor. Okay. What is a tensor? Well, it's a physical kind of mathematical object that has a relationship with a coordinate system. Can you think of another mathematical object that has an implied relationship with a coordinate system?
A vector.
A vector, exactly. So 5, 4, -2 is a list of numbers. Okay, there's no vector properties implied. But if you take this to mean 5 times, this unit vector plus 4 times this unit vector minus 2 times this unit vector, this is a vector. Okay? So in other words, the relationship between the list of numbers and the coordinate system is what makes it a vector. Okay, so tensors are the same way. So 2, -4, 6, 0 is a matrix. However, if you interpret this matrix to mean 2 times, oh God, why did I even start this? I didn't think about this before class. Plus -4, I think I'm using this notation right. I'm going to quit while I'm ahead. Okay, so notice that what I have, you don't have to understand anything about this. I don't either. But what you have to understand is here, when we're talking about a tensor, each one of the elements of this matrix has a relationship with those coordinate axes. Okay? Is a tensor. So the relationship between the matrix and the coordinate system is what makes it a tensor. Okay, so that's the first thing. A tensor is like this mathematical thing that has a relationship with a coordinate system. So now let's think about how we would want to describe local loading. We want to describe the loading of an object at a point, the internal loading of an object at a point. So think of internal loads. So how many times can I draw this picture and your engineering careers a lot because it's so rad looking. Okay, so imagine flexing this stick, and it's going to break somewhere in here. Okay, and let's say at a single point on the red line, we want to describe all the loads applied to that point by the surrounding loads, by the surrounding material. Okay. So how are we going to do this? Well, we're gonna first think of a finite cube that around that point, and then we're going to use a limiting procedure to make it smaller. Okay, seems reasonable, right? So let's say we have this finite cube. In the middle here is the point of interest. And now let's think about all of the loads that have to be applied to this cube by the surroundings. Okay, so what would that look like? Well, on each face, there's going to be a force vector and there's also going to be a couple vector. Are you with me on that? Same thing over here. I'll just draw the ones that are peeking out. Same thing here. Everyone remember that couple notation? So here you have force, and I'm just trying to make it look, when you look back at this, like, okay, on every one of these faces, we have 3 force components and 3 couple components. How many faces are there on a cube?
6.
Yep, so 6 faces. And each face has 3 components of force and 3 couple components. And now let's start thinking about what happens as we take the limit in size, as this goes down to 0. Well, the first thing that happens is, what's the limit of the force on each one of these faces as the size goes to 0?
0.
0, that's exactly right. So the force components go to 0. Okay, well, that's not helpful to us I mean, we're not going to take the time to describe this thing by a bunch of zeros. You know what I mean? That's not helpful. So instead of thinking about the forces applied, describe these forces or describe these loads as force per area components. Okay. Well, now as you take that limit, you know, the force goes to 0, but the area goes to 0 too, and you end up with finite values for these. Okay, so now we're getting at something useful. Yay. Okay, now what about the couples? So if you remember in statics, I did a, like, part of one day, I did a little derivation of the moment produced by a couple, and it ended up being basically like the force times the distance between them was the magnitude of it, times the perpendicular distance between them. But okay, so now we have our limit of force per area. Okay, so now think of the couples. And instead of couples, we're going to think of instead of thinking of couples exactly, think of sort of like the force per area crossed with, what did I call it? Like a row vector, something like that. I think I had the row over here. Don't worry about the details of this. But so now we have like if we were just thinking about the couples, of course they go to 0 if the forces go to 0. So instead we're going to think of something like a couple, but we'll divide it by the area. Okay? So what happens to that in the limit? Well, the force per area, I said, limit is finite. But notice that row vector is going to 0. So this thing still goes to 0. Okay? So the limit still goes to 0. Because the distance between the equal and opposite force per area goes to 0. Okay, well, we're starting to reduce this a little bit. So now that we have this limit, so the loading at this point, we can just think of as defined by those force components. That the force per area component. Okay, so now we have this infinitesimal cube. I'm still going to draw it big enough to see details. infinitesimal. Okay. So now the loads that we're worried about on this look like this, 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 you know, on all those faces. So we can think of this as kind of the definition of the stress. How many values define the stress now at this point? So this is our starting point. Yeah, right. We have 6 faces, 3 components on each one. And so we have 18 values. But we can reduce it a little more than that. We can keep reducing it. So more reductions. So first, in order for this to be in translational equilibrium, so in other words, in order for the center of mass not to accelerate, force components on opposite faces must be equal and opposite. Okay, we're not going to go through a proof of that, but I think everyone can agree it's plausible. If you have this one that's pointing to the right, if that's big and the one pointing to the left is small, this thing's going to accelerate. Okay. And so, well, how much does that cut the number of values down that we need to define this? In half, exactly. So now we're at 9 values. And there's one more type of equilibrium we can require, rotational equilibrium. And what's required for this to be in rotational equilibrium? It requires that for all the, so you can think of there being like a distinction between the components that are going into or out of the face and the components that are parallel to the face. Okay. So all the components parallel to the face have to obey, so they have to go like this, whatever direction you're looking at this thing. The tails have to be together and the heads have to be together. Okay. And so that reduces this now to, we were at 9. This reduces it to 6 values. Okay? And these 6 force per area values make up the stress tensor. Okay, so we have you can think of a stress tensor two ways. Two equivalent ways. Question?
Sorry, would you be able to show like on the cube those
Yes.
6?
Yes. Yep, I'm going to do that right now. So on the cube, we have so this is the way we're going to this is the way we're going to label these values. The face that you're on, so we only have to label the positive faces. Okay, the positive X face, the positive Y face, and the positive Z face, because we know the opposites are equal and opposite. And the way I'm going to label them is if we're on the X face, the first subscript of a value is going to be X. And then the second subscript of a value is going to be the direction the component is. Okay, so
Sorry, would you mind just scrolling up a little bit?
Yeah.
Please? I guess I missed a lot. I'll just.
Okay. Okay, so so the first subscript is the face that it's on. The second subscript is the direction of the component. And we're thinking of a coordinate system like we're used to. X, Y, Z. Okay. All right, so the one over here on the right side, that's the X face. You with me on that? And so the first subscript for all of these is going to be X. And then the one pointing to the right is in the X direction. So that has a second subscript of X. The one pointing up is pointing in the Y direction, so that's XY. The one pointing towards us is in the Z direction, so that's XZ. Are you following that naming convention there? And then what about on the Y face? So this is all of these, well, you can think of these as starting with Y, right? So this is Y, Y. Now, for rotational equilibrium, these other two, we could write this as YX and YZ, right? I mean, that's what the naming convention says. But for rotational equilibrium, that has this one that's pointing in the X direction has to be equal to the sigma XY that I already did. So I'm going to write this as sigma XY, even though by the naming convention it should be YX.
We generally want to have X as our like primary, or like it'll be XY, not YX for the.
Yeah, that's what people tend to do. Yep. And then so this one, we could write this as YZ. I guess we will write this as YZ. And now we'll go to the third face. We have sigma ZZ. And because of the the rotational equilibrium. The one on the z face pointing in the x direction we'll call sigma xz instead of zx. And the one pointing in the y direction we'll call sigma yz instead of zy. And I'm going to call this the stress cube. Anytime you see a stress tensor, you can write out the values in the stress cube. Okay, to get a visual idea of what's going on. And I'm always going to, no matter what the orientation of the coordinate system is, I'm always going to draw it like this. But notice that this cube would have to be oriented with those coordinate axes. Okay? To do math with this, the equivalent form is the stress tensor, and that looks like this, a 3x3 matrix, sigma xx, xy, xz. And now this is a symmetric matrix because of the rotational equilibrium. So on the next row, we start with xy again, yy, yz, and then the third row, xz, yz, zz. And this is the stress tensor.
Probably a dumb question, but what about the other three faces?
Those other three faces, we don't need to give those values because we already know that those are equal and opposite to the three that we see.
Yeah.
Yep.
So why, and I know I missed this, but why is the right component, the x component, the same as the y? Why is the component going to the right on the top face the same as the component going up?
Because that's required. These have to be equal and opposite like this in order for this not to spin. So
Okay.
it's a rotational equilibrium requirement.
Okay, and you're just ignoring the back side.
And I'm ignoring the back ones because those have to be equal and opposite of the front
Also.
ones for translational equilibrium.
Yeah, that was the one right above this.
Yeah. Yeah, while you were out doing whatever you're doing, partying or whatever, we were in here talking about this stuff.
Out there thinking up sarcastic remarks.
Yeah, exactly. Okay, so there's some important stuff about this that you can see really clearly from the stress cube. These, the ones on the diagonal, are called the normal stresses. And you can see from the stress cube why they're called that. XX, YY, and ZZ are the components that are coming perpendicularly out of the positive faces. Okay? And the off-diagonal elements are called the shear stresses. Okay, so whenever we talk about normal stresses and shear stresses, this is what we mean. And why do we call these the shear stresses? Well, if you think about, if you go back to like statics when we define shear forces in beams, these stresses are doing the exact same thing that those shear forces were doing in internal loads. Okay? It's basically doing what scissors do. It's like you're trying to cut this thing at that point. Okay, so mathematically, there are two ways to represent the stress, and we'll have to use them both in different, bless you. The first one is the stress tensor. I guess I'll write that again here. It can't hurt to get this under your fingertips a little. So sigma xx, sigma xy, sigma xz, sigma xy again, sigma yy, sigma yz, then sigma xz, sigma yz, and sigma zz. Okay, and how often when you have a stress tensor can you write a corresponding stress cube for it?
When you have all the values?
Yeah, always. So remember that that's always, like, that stress cube is always a representation of a stress tensor. If you have one, you have the other, okay? That was a weird way to ask that, but now the second way to represent the stress mathematically is the Voigt stress, the Voigt form. Okay, Voigt stress. And in this case, I mean, we're just writing, so that stress tensor, notice it has 9 values, but only 6 are independent. You only need the 6 values. The Voigt stress just writes down the 6 that you need. And here is how you write them down. So sigma xx, sigma yy, sigma zz. And then I think to anybody who picked the order of the shear stresses would do it in the same order. So of course they do it the exact opposite order of that. Sigma yz, sigma xz, sigma xy, like insane people would do.
I thought, because you said, it's just like how we went, and I went and wrote it exactly the different way that you said it. So
Yeah.
exactly as you said it.
Yeah, right. Yeah. So, I mean, that's honestly still, all these decades later, that's still how I think of it, as think of how a sane person would do it and then do it opposite.
Is there like a mathematical reason where it makes sense?
Not that I'm aware of. I don't think so. I think it could be in any order, and then the math is all defined just on whatever order you choose.
I think Voigt was mad because his name is weird.
Yeah, I know, with the G in there. And people probably ask him about John Voigt. Often the shear stresses will be written instead of as sigmas, as taus, and it means the same thing. So I'm going to rewrite both of these. So the Voigt stress also a lot of times you'll see like this. And then tau yz, tau xz, tau xy. And go back to the stress tensor, and you can write that sigma xx, tau xy, tau xz, tau xy, sigma yy, tau yz, tau xz, tau yz, sigma zz.
What is the tau representing?
It's just choosing a different variable for the shear stresses, I guess. So just visually, you don't mix them up because they're sort of different in some ways that we'll see. Okay.
It's a different symbol for the different type of stress.
Right. Yep. And so then if you did the stress cube, corresponding to that. You would write that as sigma xx tau xy tau xz sigma yy tau xy tau yz sigma zz tau xz tau yz. Okay, so as you can imagine, a lot of what we're going to do at the start is just, you know, a lot of having stress tensors and drawing the stress cube and going back and forth until it's kind of second nature. It's something, you know, an elementary school kid could do, but you have to just get it under your hands, you know. Okay, the units for stress. It's force per area. Which is the units of pressure. And so that means that the SI units are pascals. Which is the same thing as newtons per meter squared. Often, so this is something important, notice. Stress will often be given in megapascals or even gigapascals. So make sure that you don't have a unit mismatch. Once you start doing calculations, because if they don't, you're going to get crazy, meaningless answers. Before I do calculations, I just always put everything in SI units. You don't have to do that, but it's a way that avoids mistakes, you know. Any questions about that yet? So let me just do a couple examples of the kind of stuff you're going to be doing. So let's say we have a stress tensor of 5, 0, -1, 0, 50, 2, -1, 2, -10. And let's say this is in megapascals. So to get this in SI units, this would be 5 times 10 to the 6, -1 times 10 to the 6, so on, okay? And we want to draw the stress cube. And B, we want to give the Voigt form. Okay, so the stress cube. Okay, XX is 5. So that goes here. I'm going to just do this in megapascals. XY is 0. And so I'm going to get rid of this one, computer. Okay, this one's 0. I'm just going to erase it. And that means I'm going to erase this one too because it has to be the same. You with me on that? Now, Z is -1. I could write that in the opposite direction or write this as -1. Either one of those is fine. You know, I could write it in the opposite direction and call it 1, or I could write it in this direction and call it -1. If you write it in the opposite direction and call it -1, that's a double negative, and that's wrong. Okay? Now we'll go to the Y face. We already dealt with the 0. The 50 is here. And then the +2 is here. And now, because of the symmetry of this matrix, we know that this one is also 2. We know that this one is also -1. And the last value is -10. Okay, let me draw this, the equivalent of this. So we have a 5 this way. Instead of a -1, I'm going to draw this way. 50, 2, the 10 is negative, so it's pointing in. You have a 1 going this way and a 2 going this way. I don't care where you start those lines.
So is that going to be a useful way to represent these?
Yes, it is going to be. And either one of those is fine.
But like by, removing all the negatives and kind of.
Oh, I mean, I guess it maybe gives you a little better, just kind of like when you draw a vector that has a negative magnitude and you just draw it with a positive magnitude in the opposite direction, you know, it helps you visualize it, I suppose, a little bit. Yes?
Bit of a silly question, but how many pascals is a gigapascal?
9, 10 to the 9, not 9, 10 to the 9. That's a big difference.
Billion Pascals?
Yeah.
But a Pascal, I mean, is like tiny.
A Pascal is small, right? I mean,
The most
So
common
mega-
use of it is kilopascals, isn't it? KPa?
for stresses, I guess it depends on the material. You know, for steel, unless you're in megapascals, it doesn't have any effect on the material noticeably at all. You know, for engineering materials, megapascals is probably more common, but for silly putty, you know, then you wouldn't get to megapascals. You guys know in the movie Back to the Future, have you seen that? And they call it gigawatts because like people hadn't even talked about giga as a prefix enough to decide how to pronounce it. Now it's like such a normal part of our life, you know?
Thanks, storage.
Yeah, exactly. Okay, and now we have to do last thing we have to do is the Voigt form. And so you write that as sigma sub v under squiggle. And for that, we'll go the XX value, the YY value, the ZZ value. And now think of a sensible way to do it and do it backwards. YZ is 2. XZ is -1. And XY is 0. And I'll give this in megapascals.
So you think of it as creating a right triangle, tracing a right triangle through the matrix.
Mm-hmm.
Oh,
Yeah, like if you follow it back to
Wow.
the corner,
Bottom
back
right,
to
and
where
then
it started.
either top or bottom, just loop back.
huh. Interesting. I've never thought about that
That's how
before.
I'm gonna do it anyway.
Okay. I'm going to just keep thinking of it as frustrating. Did you have a
I
question?
was gonna ask what the V stands for, but probably void.
Oh, void, exactly. Just so, yeah. That's so in later notation, when I talk about multiplying matrices and stresses and stuff, you know what form the stresses have to be in, right? And if there's no subscript there, then assume it's a tensor. Okay, any other questions? All right, that's it. I'll give you some stuff on this to do, and Martin Luther King Jr. Day on Monday, so no school. So I'll see you on Wednesday.
That'll be